All right. In 8.1 part 1, we talked about how to use the alternating series error bound to approximate the error for an alternating series that converges. And one thing that I really want to point out is that even with the alternating series error bound theorem, we were still not able to actually say what the error was. We can't say the error equals this number. We gave an upper bound. We said that the error is at most some number. And the reason that we can't find the exact error is because if we could find exactly what the error was, then we could actually find the sum, which would mean we wouldn't need to talk about the error to begin with. So the goal when we're talking about error is to be able to say our approximation, or if you approximated using this many terms, we can say it's within this error of actually being the correct sum. It's at most this far off. And that's really the idea, is being able to guarantee that our error is not off by more than some number. That's the idea behind error. And we used that idea first in 8.1 part 1 when we were talking about alternating series error, but now we're going to use that to talk about a different type of error. So alternating series error is great, and if I have an alternating series that converges, that is the error that I'm going to choose to use unless a problem specifies otherwise. The issue that we run into is that not every series is alternating, and there are series that do not alternate that do in fact converge. So how do we approximate error for those series? How do we approximate the error for a series that could be represented using a Taylor polynomial? And that is where LaGrange error comes in. So before we jump into actually looking at how this error works, we're going to do a little warm-up and freshen our skills on e to the x. So go ahead and write out the first 5 terms for the Maclaurin series for e to the x. You don't have to make the table. You can just write out what you should know the elementary series is for e to the x. And then find the partial sum of the first term, of the first and second term, of the first, second, and third term, all the way up to the first 5 terms for approximating the value of e to the first power. So what I mean here, and a couple of things that I'm just going to point out as reminders, is that when it says a Maclaurin series, that means that our center is 0. And here, where it says e to the first power, that means we are using x is equal to 1. So go ahead and pause the video, write out the series, and then find those partial sums. All right, so here I have written out e to the x in case you have forgotten the series for e to the x, which you should know. And then I substituted 1 in for x in this lower series. And then I just calculated the partial sums of the first term, of the first 2 terms, etc. So something that I want you to notice that is very different than an alternating series is that for this series, we're not oscillating back and forth between an overestimate and an underestimate and an overestimate and an underestimate as we were with an alternating series. We are consistently below the sum. And that should make sense because every single term is being added together to get closer and closer to the sum, meaning the only way to actually get to e to the first power, which is what we're trying to approximate, the only way to get there is to add an infinite number of terms together, which we can't do. So the more terms we add, the closer we get to the actual value of e to the first power. But look at each of these numbers. We know, if we grabbed a calculator, what e is. We know that 1 and 2 and 2.5 and 2.6 repeating and 2.708, all of these numbers are actually underestimates because we're never subtracting anything from this series. Everything is being added. And if we're never subtracting, and this series is equal to e to the first power, if we go to infinity, every single partial sum is going to be an underestimate. So this infinite sum is not an underestimate, but every single partial sum is going to be an underestimate. And I just think that that's important to point out that the series that we're talking about now don't behave in the same way that the alternating series behave. So I'm going to zoom out real quickly and try and make some stuff make a little bit more sense before we come back in and formalize it. So suppose we had a function f of x, and that function was represented using a Taylor polynomial that is centered at c. So we know from last unit that we could write this as follows. So if I used a Taylor series to define f of x, I would get this. Now, if we could calculate infinitely, this would be an exact value of a function. But what we typically do is we look at a polynomial, a Taylor polynomial, or we look at part of a function. So if I stopped at the nth term, then I could call this my Taylor polynomial of degree n, t sub n of x. And I could say that f of x is equal to this Taylor polynomial approximation plus some remainder of x. Or I'm going to put r sub n of x. So this should make sense. The entire function is equal to whichever part I'm using to approximate plus whatever I didn't include, right? The rest that's going up to infinity. And that remainder is what we're interested in. That is our error, or that is our remainder that we're talking about. How far away is this approximation from the actual sum? So that's what we're considering when we're talking about error. So the point of what I'm showing you here is what we're talking about when we're talking about the error. So if you come over here, and I'm going to try and zoom back in without getting you too dizzy here. This right here, r sub n of x, is the error, or the remainder. It's the part of the sum that we're not including. And our goal is to come up with a number that we can say the error is at most this. Again, our sum is wrong or off by at most this number. That's the purpose of what we're going to be doing. So I really want to hit hard on that notation there. So let's analyze the other parts of this remainder theorem here. So this remainder theorem in this box here. So r sub n of x is our error, or our remainder, is less than or equal to, because we can't find the exact error, because if we could, then we could find the exact sum and we wouldn't need to have an error at all. This x minus c to the n plus 1 over n plus 1 factorial, that should look really familiar coming right out of the Taylor polynomial, looking at the next term. The most confusing part is this part right here. And that's what I want to spend a little bit of time talking about. And I'm actually going to refer to that as m. And what m is going to do in this formula is m is any upper bound of the next derivative evaluated at the center that is on the interval between x and c. So let me actually write that out in words so that you can see what I'm trying to say. So again, m is an upper bound of the n plus first derivative on the interval between x and c. So the hardest part of what we're about to do is that we actually have to find this value, this magical number, I like to call it the magic z. We need to find this magic z value so that we can identify a maximum value on the interval between x and c, c being the center. We want to choose a number that is friendly. The whole point here is to be able to calculate error, to say that the error is at most this number, and we want to be able to do that efficiently. So we want to choose friendly numbers, or I like to call them kindergarten numbers, numbers that my 5-year-old would actually be able to say, oh, I know what that number is. And that's going to sort of be the difficult part. We also need to make sure that when we are choosing this number, which I know I haven't talked in detail about yet, but when we are choosing this number, we're choosing a number that is close but slightly larger than the actual maximum value. So I also just want a couple of reminders here that c is our center and x is the value that we're approximating. And those pieces are going to come into play a little bit in just a minute. So let's go ahead and work through some examples and see if that helps you get an idea of what I'm talking about here with this m and how to calculate that and how to use that to then calculate LaGrange error bound. I also do want to mention that LaGrange error bound is also referred to as the Taylor remainder theorem, and it says that up here. Those two are used interchangeably, which makes sense since we're talking about Taylor polynomials to call it the Taylor remainder theorem. Just making sure we know those semantics. So back to what we were talking about a little bit in the warm-up. Suppose we kept going with our partial sum approximation and that we actually approximated e to the first power using the first 7 terms. So a couple things to point out. We're saying that a 7th degree Maclaurin polynomial was used to approximate e to the first power. So right away, we know that c is 0 because that's what it means to be a Maclaurin polynomial. We know that x is 1 because that's what we're approximating. We're approximating e to the first power, which means x is 1, since we're using the Taylor series for e. And we know that we used a 7th degree Taylor polynomial, so I know that my n value is 7. So let's put these pieces together to look at our remainder. So I can say that the remainder for the first 7 terms, I could also just simply write the word remainder. That didn't look like absolute value. Let's try again. Is less than or equal to f of n plus 1 of z times x minus c, which in this case is 1 minus 0. Actually, why am I putting n plus 1? I know what n is. N is 7. So n plus 1 is 8 of z times 1 minus 0 to the 8th power. That's all in absolute value, and that is over 8 factorial. So everything that's in here is a number that has a value with the exception of our m piece. So how do we go about finding our m value? So the first thing we want to think about is, what is the 8th derivative of the function we're approximating? What is the 8th derivative of e to the x? Well, it's just e to the x. And we are looking at it on the interval between 0 and 1. And we are trying to maximize what we're talking about on this interval. We're trying to maximize our value between 0 and 1. So that is going to happen when x is equal to 1, which means our m value would be e to the first power. Now, e to the first power is not a friendly number. And I also want to point out that if we knew what e to the first power was, we wouldn't need to use a 7th degree polynomial to approximate it. So e to the first power is not something that we commonly know. So what we want to do is we want to use a value that we know to be more but close to e to the first power. So I know that e is approximately 2.7, which means I could let my m value be 3, right? I think I mentioned kindergarten numbers are our friend here. We're going to let our m value be 3. And now that I've chosen my m value, I can substitute that into the remainder expression that I have up here, and I can simplify that. So the absolute value of the remainder is less than or equal to, our m value is 3. I'm going to write this, even though it seems silly, 1 minus 0 to the 8th power is 1 over 8 factorial. And now most of the time, this is really what you're going to be asked to do. You're going to be asked to put a limit on this remainder, to put an upper bound on it. This specific question said, show that the error is less than or equal to this. And I will tell you that 8 factorial is 40,320. So we have shown this to be true. So let's look at a couple more examples and see if we can really solidify this process of setting up the LaGrange error bound and finding our m's. All right, number 1 says, approximate the error using LaGrange error bound for a 4th degree Maclaurin polynomial for e, the 10th root of e, which I'm going to rewrite as e to the power of 1/10. So what do we know? We know 4th degree, so n is equal to 4. We know Maclaurin, so c is equal to 0. We know we're approximating e to the 1/10, so x is equal to 1/10. So let's go ahead and set up our remainder. Our remainder is less than or equal to the fifth derivative of x, or z, more commonly you're going to see a z here, times x, which in this case is 1/10 minus 0 to the fifth power. All of that's inside absolute value over 5 factorial. So in order to complete this, I need to find a value for m, which is just this right here. So let's first consider, well, what is the fifth derivative of the function that we're approximating? Well, we're approximating e. The fifth derivative of e to the x is just e to the x. And we're approximating it on the interval from 0, which is the center, to 1/10, which is the upper bound. And where is e maximized between 0 and 1/10? Well, it's going to be biggest at 1/10. Now, we don't have any idea what e to the 1/10 is. That's the whole purpose of this problem. What we do know for sure is that it's less than e. So we could, as we did in the example above, I think we could with certainty say that this is less than 3. If I took the square root of 2, which this is a little bigger than that, I think I could also say that this is likely less than 2. So I might also be able to use 2 here. I don't want that to look like 3 squared. But if I'm just trying to be safe, I know for sure e to the 1/10 is less than e, which means it's less than 3. So I'm just going to go ahead and use 3. And I could use a calculator to figure out if e to the 1/10 is less than 3. But if I could use a calculator, then why would I be calculating this error anyways? So we can say that the error, the absolute value of the error, or the remainder, is less than or equal to 3 times 1/10 to the fifth power over 5 factorial. And we really don't have any reason to simplify that. So we're identifying what we're given in the problem. We're setting up the remainder using LaGrange error bound. We're identifying what our m is, and then we're simplifying as needed. So let's go ahead and look at number 2. We're going to use LaGrange error bound for a 5th degree Maclaurin polynomial for sine of 1. So why don't you go ahead and identify all of the information that we know. Don't try and find m quite yet, or maybe if you really want to challenge yourself, you can, but go ahead and pause the video and identify what we know based on the problem. So here we know that n is 5. Maclaurin means that c is 0. We're approximating sine of 1, which means that x is equal to 1. Now go ahead and set up your remainder. So here we have set up our error approximation. And now we need to look at our 6th derivative. So over here, we're going to find our m. So something I want to point out to you, we're trying to maximize the derivative of our function over the interval that we're looking at. So we're talking about on the interval between 0 and 1. And our original function is sine. So I could, if I really wanted to, take 6 derivatives of sine, which I believe would get me to negative sine of x. And I could approximate what is the max or the min for sine, negative sine of x. But the beauty of sine and cosine, whichever derivative we're at, whether they're positive or negative, is that we know how sine and cosine behave. They are so predictable. We know that sine and cosine are always trapped between 1 and negative 1, which means if we want to maximize, why not just let our m value be 1? 1 is the biggest, we don't know exactly what's happening, but 1 is definitely the biggest approximation that we could use for sine. And it's definitely a kindergarten number. It's a number that we feel incredibly comfortable plugging in. So I'm going to put a 1 here, times 1 to the 6, which is still just 1, all over 6 factorial. So this is just 1 over 6 factorial. Now, something I want to point out to you, this was by LaGrange error bound. But sine is also an alternating series. So we could have found the error using the alternating series error. Now, this problem specifically said in the directions not to do it that way, to use LaGrange error, but I just want to freshen up on that alternating series error since we can use that on this problem. So what we would do here is we would say that the remainder of the fifth term is less than or equal to whatever the sixth term is. And the sixth term, based on the Taylor polynomial for sine of 1, would just be 1 over 6 factorial. So it happens to be that these two approximations are the same. That's not always true. Sometimes one will be better than another, and it's a really good thing to compare. If you have the choice, just compare the small amount of work that I did down here for blue to all that work I had to do up top. I would definitely choose A as C if I had the choice. All right, for the rest of this lesson, we're really just going to work through some examples and hopefully solidify in this concept. All right, number 3 says approximate e squared using a third degree Maclaurin polynomial, P3 of x. So you are actually going to do that approximation. So why don't you go ahead and pause the video and use a third degree Maclaurin polynomial to approximate e squared. So here I have set up the polynomial. In terms of x, I have substituted in 2 and gotten an approximation for e squared, 6.3 repeating. Now, the second part of this question says, what is a Lagrange error bound for e squared minus p sub 3 of x, which is literally just asking you for the same thing. This is just different notation, and you really should get comfortable to seeing it all these different ways. This is really just asking you how far away are we from the real thing. So this is just big fancy notation for still the error or the remainder. So go ahead and set that up using what we know from the problem. So here's that setup. Now I need to find my m value. I meant to pick a different color here. I need to find my m value here. So e to the x, the fourth derivative is still going to be e to the x. We're looking at that between 0 and 2, so we're looking for e squared. E squared is what we're trying to approximate. I know that e is less than 2, which means that e is less than 3, which means that e squared is less than 3 squared. So why don't we use 9 as our m value? So let's go ahead and substitute that in. And there I have my error, and you could leave it just like this. This would be our error bound. Something I want to point out, and I hope you noticed, 9 times 2 to the 4th over 4 factorial, this is a pretty big number. And actually, if you plug that into a calculator, that's 6. 6 seems like a really big error, especially considering the error that we have been looking at in previous problems. It should make sense to you that this problem has a big error because it was centered at 0 and we were approximating x equals 2. If we wanted to better approximate e squared, we should center the polynomial at a different number besides 0. Using a Maclaurin polynomial is always nice. We love having all those zeros in there, but it doesn't make for a great approximation if we're trying to approximate e to the second power. So I just wanted to point that out, whether or not you noticed it. Let's look at the next one. So here we're given some f of x whose Taylor series converges for x equals 2. We are given some information about the fourth derivative of x, that the absolute value of that is less than or equal to 4. And part A is asking us to find the Lagrange error bound if a third degree Taylor polynomial centered at x equals 1 is used to approximate f of 2. Now notice we are not being asked to approximate f of 2, we're being asked to approximate the error. So go ahead and pause the video and see if you can figure out what to do here and at least set it up. And if you're stuck at what to use for m, I can help you out with that in just a minute. So here's the setup. And this is hard to read, but this does say 4 here. Now, the only piece of information that we need to actually approximate this error is this number. And they are telling us what to use here in the problem. They didn't specifically say use m equals 4, but anytime you see this notation, that is what it's subtly saying. Use m equals 4. So go ahead and plug 4 in and then simplify that. It's going to simplify pretty nicely, and I think you may see that already. 4 over 4 factorial, which is going to be 1/6. So our error is 1/6. That's a pretty good error. Part B says, if t sub 3 of x is equal to 5 from part A, meaning the Taylor approximation was 5, determine the range of possible values for the exact value of f of 2. So this is saying if the polynomial approximation came out to be 5, what could we for sure trap f of 2 between? So thinking about this, we know that f of 2, we want to trap it between two numbers. And basically what we're going to do is we're going to take 5, which is the value that they're giving us here, and we're going to add and subtract the error. If the remainder is at most 1/6, then we can just go up and down 1/6. Then you could leave this as 5 plus 1/6 and 5 minus 1/6, or you could actually simplify it 29 over 6, which is not required 31 over 6. So we could actually trap the value of the function in between two other values. All right, number 3 has some great review from Unit 7, or sorry, number 5 has some great review from Unit 7. So I encourage you to pause the video. I'm going to recenter this. Pause the video and work through that problem on your own. So hopefully you've had a chance to at least complete parts A and B, and you can go ahead and look over those and then pause the video again and see if you can work on part C. And if you're stuck, that's okay. I'm going to work through it with you in just a minute, but go ahead and at least set up the LaGrange error bound. So hopefully you could get yourself here. Now, to do some work to find our derivative. Well, first of all, we need to know what the fifth derivative of x is. And this is going to be kind of a pain because it's not a lot of work, but it's definitely more work than e to the x, where we could just simply call it e to the x again. So originally the function is natural log of x. If I take the first derivative, I get 1 over x. If I take the second derivative, I get negative 1 over x squared. I'm just using the power rule. 2 over x to the third. The fourth derivative is going to be negative 6 over x to the fourth. And the fifth derivative is going to be 24 over x to the fifth. So we want to maximize 24 over x to the fifth between our center and the value we're approximating. So 1 less than or equal to x less than or equal to 1.3. We want to maximize it here. So think about what we're doing here. We're dividing 24 by something. If we want this to be bigger, we want to divide it by the smaller number. So we can actually use that our m value, if we plug 1 in here, our m value is just 24. So this is going to give me that the absolute value of the remainder is less than or equal to 24 times 0.3 to the fifth power over 5 factorial, which I'm going to tell you is 0.000486. Part D says find the number of terms from the Taylor polynomial needed to approximate f of 1.3 with a remainder of less than this. Well, we just got pretty lucky. That is already true, so we can definitely say, based on part C, we can use 4 terms. And this question doesn't ask us for the fewest number of terms, so we don't actually have to check and see, well, would 3 terms have done it? The question didn't say, tell me the fewest number of terms. It just said, find the number of terms to approximate it. So 4 terms would work just fine. We proved that on that part before. All right, I'm going to encourage you to challenge yourself on 6 and 7 and go ahead and work through them both and then unpause the video and see how you did. So for number 6, you can pull out that n is 3, c is 0, x is 0.1. Since we're approximating sine, we can use that our maximum value, our m, is 1. So we can get that the LaGrange error bound says that the remainder is less than or equal to 0.1 to the 4th power over 4 factorial. Now, number 6 also asks us to compare using ASE. So let's go ahead and do that. Alternating series error would say that we just need the fourth term. So the remainder is less than or equal to the absolute value of the fourth term. And the fourth term would just be 0.1 to the 5th power over 5 factorial. Because remember, sine is a function that only has odd exponents, and this is a better approximation because it's smaller. So just something to notice. All right, go ahead and pause the video and work through the last one. So here we do need to do a little bit of manipulation to figure out what the x value is that we're approximating. But if we're using e to the x minus 1 and we're approximating e to the 0.2, we can say that 0.2 equals x minus 1, and that's going to give us the x value that we're going to use, which is 1.2. Here we've set up our remainder. Now we need to just find a value for m. So we know that we're looking at x values that are between 1 and 1.2. Our center and the value we're approximating. If we look at the third derivative of e to the x minus 1, we still get e to the x minus 1. If we plug in 1.2, we get e to the 0.2. So based on the problem we did on the front where we looked at e to the 1/10, I know that I can use an m value of 2. And if you didn't know that or you had no prior knowledge, you could use an m value. For sure, that would be 3. That would work as well. 2 is more precise, but you have to use what you know based on the problem, because in theory, you should not need a calculator to do this math. So this is going to give me 2 times 0.2 to the 3rd power over 3 factorial, and I see no reason to simplify that. So key ideas in this section. The LaGrange error gives us the remainder or the error or the difference between the actual sum and the sum we're approximating using a Taylor polynomial. You need to make sure that you understand how to set up that remainder and how to find that m value, which needs to be bigger than the value that we're trying to approximate. Be on the lookout for kindergarten numbers or magic numbers like integers and whole numbers that are going to make our lives much easier when we're trying to approximate something that's maybe not so easy to approximate. Make sure to write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.